Okay, in this presentation, I'm going to outline how we can support seamless VM mobility using collection of either existing IETF standards or technologies that are on IETF standards track. So let's start by introducing the reference model. And we start this reference model by just looking at a single data center. So what you see at the edge here is a collection of servers that host virtual machines, VMs. These servers are connected to the network using top-of-rack switch stores. And there is a cloud in the middle, intra-data center cloud. I'm not going to talk too much about what's inside of this cloud. Suffice to say that it could be as simple as a single high-performance queue fabric, or it could be actually a three-tier network with access aggregation and the core. There are a couple of boxes here labeled as data center border routers, and you'll see the next slide their role. You'll notice that I colored different VMs in different color. And for now, you may think about colors as VLANs, and you'll see in a couple of slides that actually colors mean something else. But for now, think about them as VLANs. Now let's step back and look at the bigger picture where you have a collection of data centers. They're interconnected by what is known as data center interconnect, inter-data center cloud. And now in this slide, you see the role that data center border routers play. These are the routers that interconnect individual data centers to the cloud. You also notice that in this picture, you see a client side where you have individual hosts that communicate with virtual machines in the cloud. So that's pretty much the basic reference model. With this in mind, let me define what I mean by seamless mobility. And in the context of this presentation, when we talk about seamless mobility, we talk about the ability to move virtual machine from one server to another, irrespective of whether these two servers are in the same or in different data centers. But what's important about this concept of seamless mobility is that as we move VM from one server to another, we are able to preserve VM's IP address and VM MAC address. And that is irrespective, as I said, whether the servers are in the same or in different data centers. Notice that this definition that I put in this slide doesn't say anything about the ability to preserve VLAN ID. And you'll see in a moment there are good reasons for that. Having said that, if you do preserve the same VLAN ID, it's OK. It's still seamless mobility. All it says that seamless mobility really doesn't care about VLAN ID preservation. I want to introduce here a couple of new concepts, a couple of new constructs that would be useful when we talk about VM mobility, seamless VM mobility. And the first concept I want to introduce is the concept of layer 2-based closed user group, which I'll call L2-based COG. So as you read the definition, I want to bring your attention to a couple of points. The first point I want you to pay attention to is that this definition of layer 2-based COG talks about virtual machines interconnected by a network. But it doesn't say anything about what's inside the network. All this definition said is that the network has to provide a specific service. And what that service is? The service is that you should be able to preserve source and destination MAC addresses of packets that travel from source to destination VM. That's all what it says. It doesn't say anything about how network should accomplish this service. It's quite clear from this definition that there is nothing which could stop a virtual machine to be a member of several L2-based COGs at the same time. In terms of mapping between layer 2-based COGs and IP architecture, a single layer 2-based COG corresponds to a single IP subnet. Now, if you think about a single layer 2-based COG as an island, then clearly you don't want communication between machines in that island to be restricted to just that island. You want islands to talk to each other. And for that, you need IP forwarding, which means that VMs that are member of one layer 2-based COG can clearly communicate with VMs in other COGs. It's just this communication involves IP forwarding. The second construct I want to introduce is the construct of layer 2 site. And at high enough level, you can think about layer 2 site is just a contiguous layer 2 network. Layer 2 site could be as big as the whole network within a single data center, could be as small as just single top of rack switch and servers connected to it. And what is important about layer 2 site is that it could host virtual machines. It could contain servers that host virtual machines that belong to multiple layer 2 based COGs. So in a sense, it's kind of a shared infrastructure. And of course, the question you may ask that if indeed a layer 2 site has servers that host virtual machines that belong to different layer 2 COGs, then how would you segregate layer 2 COGs within a single layer 2 site? Well, we rely on layer 2 mechanisms, specifically on VLANs. So for the rest of this presentation, I'll be focusing on virtual machine mobility between servers that are in different layer 2 sites for a very simple reason. Because if the servers are in the same layer 2 site, then I would assume that pure layer 2 mechanisms would be sufficient to provide seamless VM mobility. Well, you may ask me a question. Why do I need to introduce these concepts of layer 2 based COGs, and why do I need to introduce concept of layer 2 sites, et cetera, et cetera? So let me try to answer this question. So why do we need layer 2 based COGs when we have VLANs? Well, VLAN is a technology, and it's one possible technology to implement layer 2 based COGs. However, it's not the only one possible. And moreover, as a technology, VLANs has certain limitations that are especially acute in the context of large-scale data center, large-scale cloud computing. The first one is that VLANs can support a fairly limited number of different closed user groups. And that has to do with just limited space of VLAN IDs. It's up to 4K. That is the limit. You cannot go beyond that. There is a second limitation introduced by VLANs, and that has to do with the size of individual layer 2 based COGs. You cannot build large layer 2 based COGs with VLANs for two reasons. One is that you would rely on ARP to resolve IP to MAC address mapping, which means you have to broadcast a packet to all the members of VLAN. And the second is that VLAN, as a technology, doesn't have a real control plane. It relies on data plane learning, which means you have to broadcast unknown. So both ARP and the broadcast unknown create certain limitations, introduce certain limitations on how big you could build a layer 2 based COG. So in this presentation, I'm going to focus on EVPN as the preferred technology to realize layer 2 based COGs. At the same time, I don't want to throw away completely VLANs, because VLANs is a perfectly fine technology as long as you understand its limitations and as long as you operate within the confine of these limitations. Why did I pick EVPN? Well, because EVPN as a technology allows me to overcome both of the limitations of VLANs that I mentioned on this slide. So with this in mind, let's go to the problem statement. So what are the problems we need to address? Well, before I'll start to talk about the problems we need to address, I want to remind you that what we're talking about is seamless VM mobility, which means that as VM moves from one server to another, VM retains its IP and MAC addresses. Well, at the bottom line here actually is very simple. The real problem we need to solve is that as VM moves from one server to another, we should be able to preserve connectivity between VM and its peers. And the peers could be either other VMs, or it could be just plain hosts that communicate with this VM. To refine it a little bit, as we talk about VM mobility, we also should be able to preserve the layer 2 based COG construct, which means that as VM moves from one server to another, it should be able to communicate with VMs in its own layer 2 based CAG without breaking the construct of a layer 2 based CAG. As I said before, VM in a given layer 2 based CAG should be able to communicate with VMs in other layer 2 based CAGs, with VM in other IP subnets. And in this case, we may talk about optimal IP routing. Notice, though, that I put optimal in quote because, in fact, we could debate for a very long time what optimal means. So in the context of this presentation, I've been very specific about defining what I mean by optimal. You could break the optimal IP routing into two parts: optimizing inbound traffic to VM, and optimizing VM's outbound traffic from VM to its peers in other IP subnets. So optimizing VM's outbound traffic is known as optimizing VM's default gateway. And what it really means in practice is that as VM sends its traffic to other peers in other subnets, its default gateway has to be in close proximity to VM's current location. To give you an example, if VM moves from one data center to another, VM shouldn't be using default gateway in its old data center. It should be using default gateway in its new data center. Now, likewise, we want to optimize routing of VM's inbound traffic. And again, using the previous example I just gave you, if VM moves from one data center to another, traffic to that VM shouldn't be going through the previous data center. It should go directly through the data center border router of VM's current data center. As I said before, in this presentation, I'm going to assume that EVPN is going to be the preferred technology to realize a layer 2 based CAGs. So let me just say a few words about EVPN as a technology. And I want to make it very clear that this is not in-depth tutorial of EVPN. It's just a very, very top-level overview of this technology. So what is EVPN? It stands for Ethernet VPN. And for those of you who know 2547 VPN, you may think about it as yet another variation of 2547 VPN, except that instead of carrying VPN IP addresses, you carry MAC addresses as network layer reachability information. In terms of next hop, it's just like in 2547 VPN, it's an IP address. And so in terms of the data plane, you use either MPLS or MPLS over GRE, and you carry traffic towards the BGP next hop. As I said, it's based on the same architecture and mechanisms as 2547 VPNs, although it does have few extensions to deal with Ethernet-specific parts. Just like in 2547 VPNs, you use BGP to exchange reachability information, IP reachability information. In this case, you use BGP to exchange MAC reachability information. What is important about EVPN and what makes it different from other technologies like VPLS is that in EVPN, you carry not just MAC addresses, but you carry a tuple, MAC address and IP address. So in EVPN, you have kind of a container that identifies VM's both MAC address and IP address at the same time. And actually, that is very important. It'll help in a variety of cases, as we'll see later. In terms of how you construct different sorts of EVPN topologies, it's the same technology as in 2547 VPNs. You manipulate route targets. And as I said before, in terms of data plane, you could use either MPLS, or if some people have aversion to MPLS, you could use MPLS over GRE, in which case the transport itself doesn't require to support MPLS. In terms of terminology, for a variety of reasons, which I'm not going to talk about, EVPN has its own terminology, but it maps one-to-one into 2547 terminology. So in 2547, you have provider edge routers, PEs. In EVPN, you have MPLS edge switches, MESs. They play exactly the same role as provider edge routers in 2547 VPN. In 2547 VPNs, you have VRFs. The analogous construct in EVPN is called EVI, EVPN instance. And of course, just like in 2547 VPN, PE could have multiple VRFs. In EVPN, a given MES could have multiple EVIs, one per each EVPN instance. There are some misconceptions already about EVPN as a technology, and in this slide, I just want to misspell some of them, not of them. And just to illustrate some of the misconceptions, I decided to pick up a couple of quotes that the previous speaker made last year at the conference in DC. So one thing which was said at that conference is the claim that EVPN would require 10 million MAC addresses in BGP. You should ask yourself, what exactly does it mean? Does it mean that a single box would need to carry 10 million MAC addresses? Well, the answer to this question, it depends. If, in fact, you want to build a single layer 2 domain, think about single VLAN that has 10 million hosts sitting on this VLAN. Yes, indeed. It would require a single box to carry 10 million MAC addresses. Of course, you should ask yourself, why would you do such a thing? Why would you build VLAN with 10 million hosts? In all other cases, actually, you wouldn't require any single box to maintain 10 million MAC addresses because just like in 2547 VPNs, EVPN relies on divide and conquer approach to address scalability, where a given MES has to maintain EVPN routes, but only for the EVPNs connected to it. And of course, the route reflectors, you could partition among the EVPNs, so no single route reflector has to carry EVPN routes for all the EVPNs. Well, there is another misconception, and it has to do with how you learn about MAC addresses. The claim was made that it does require data plane learning. Well, the truth of the matter is that data plane learning in EVPN is certainly one possible option, but it's not the only one possible. And just read the spec. So the point I want to make from this slide is that when you hear various claims about EVPN, I would suggest you take them with a pound of salt, not with a grain, but with a pound of salt, and check them against the spec. Now, with this in mind, let's return to our topic and start to talk about how we're going to solve layer 2 extension problem. Well, the solution to the layer 2 extension relies on EVPN, because in fact, what we're going to do, we're going to use EVPN as the technology to support layer 2-based COGS. So if a data center, network within a data center, is a single layer 2 site, then in this case, EVPN MPLS edge switches, MESs, would be placed on the data center border routers. But as I said, individual L2 sites could be as small as a single top-of-rack switch TOR with the servers connected to it. And in this case, top-of-rack switches are going to act as MESs. And in this case, EVPN is going to handle VM migration between servers that could be either in the same data centers or servers that are in a different data centers. Now, in the case where individual L2 sites formed by top-of-rack switches with its servers and top-of-rack switches act as MESs, data center border routers act as route reflectors for the MESs within its own site, within its own data center. So in a situation where you have a single layer 2-based COG and it spans multiple data centers and top-of-rack switches act as MESs, what will happen is the data center border routers in one data center will receive EVPN routes from the MESs because MESs act as route reflector clients and data center border router acts as a route reflector. And they just re-advertise these routes to other data center border routers in other data centers. And of course, in other data centers, data center border routers acting as BGP route reflectors will re-advertise these routes to individual MESs. An alternative to this, which would greatly improve scalability of their overall system, is for the data center border routers